in this video we're going over our next project, which is social networks and integer programming. So in last week's project we found out how to solve for a minimum spanning tree, which is a special type of subgraph that we can grab from larger whole graphs. Well, this week's project is no different. We're looking at three new types of special subgraphs: the clique, the minimum dominating set, and the k-plex. And it turns out these are slightly hard subgraphs to actually solve for. But there's a trick we can use in order to make the solving easier, and that's integer programming. So essentially what we do is we treat each node to be a 1 or a 0. We treat a node as 1 if it's actually included within our special subgraph, and we treat it as a 0 if it's not within our subgraph. And by treating our nodes as zeros and 1s, what we're able to do is we're actually able to create a list of inequalities that we can solve for simultaneously. And when we solve them, we're actually able to get the nodes of our special subgraph. And so MATLAB actually has a built-in program called intln-prog, which is going to help us solve all these systems of inequalities. And it really turns out this week's project is just a project of can you follow directions. What you're going to be doing is you're mainly going to be copying what the PDF has and then inputting in the arguments correctly for intln-prog. And you're just going to do this 3 times, one for each of the special type of subgraphs. And it turns out it's even easier than just copying. For example, upper bound, lower bound, BEQ, AEQ, F, and incon are going to be really simple arguments. You don't really have to think about them. Where the real challenge of this project comes is when you have to actually use the arguments A and B in order to do this larger solving of systems of equalities. Because A and B actually hold, and A especially, hold the inequalities that we actually have to create in order to solve for each of the special subgraphs. So what I want to do is I want to go over each of the 3 types of subgraphs, tell you what they are, and then I'm going to give you some hints on how to actually construct the system of equalities, or how to construct A. And so first, let's go over cliques. So what are cliques? Well, cliques are subgraphs where nodes in that clique are connected to every other node. So here's an example. A clique inside this graph here is A, B, and C. And so as you can see, A is connected to every other node in the set, B is connected to every other node in the set, and C is connected to every other node. And when I mean connected, I should clarify they're adjacent to one another. So they have an edge that's directly connecting them. And so that's what a clique is. Every single node within the set is connected or adjacent to every other node within the set. And so now, how are we going to represent this using a system of inequalities? Well, what we're actually going to do is we're going to set up inequalities that show node pairs that aren't adjacent to each other. And so I've given you A and how it's going to look for this graph. And so then you can manipulate it for the larger graph you're going to have to solve for. So as you can see here, the first entry is 1, 0, 0, 1, 0, 0. And so what this is essentially saying is node A and node D are not adjacent to each other. And as you can see, that's true. There's no edge directly connecting them. And then, as you can see here, the next one is node B and F are not adjacent to each other. And well, that's true, right? There's no edge directly connecting them. And what you're going to do is you're going to keep adding these series of zeros and ones over and over and over until you add all possible non-adjacent node pairs. And so, how do you get to this point? Well, the first thing you're going to need to do is you're actually going to need to construct the adjacency matrix. And you guys know how to do this, right? This is just saying which nodes are next to each other. And so essentially what we're going to do is you're going to have nodes A through F and then nodes A through F. And then you just have to put zeros and ones if the nodes are adjacent or not adjacent. And from that adjacency matrix, you should be able to grab this. That's just going to be using a couple for loops or a while loop, however you decide to do it. And then once you've created A, right, where we show all these node pairs that are not adjacent, well, B turns out is pretty simple. All you're going to be doing is constructing a ones matrix that's the size of A, but in the first dimension, and it's only going to be 1 row long. So that's not too complex. The hard part, again, is creating A, the systems of inequalities. But remember, all you have to do is you're going to take your adjacency matrix and figure out algorithmically how to include all these non-adjacent node pairs as these zeros and ones. So not a huge deal. And so the next special type of subgraph we have is a minimum dominating set. So again, let's go over qualitatively. What is a minimum dominating set? As you can see here, we have an example of C and E. And well, minimum dominating sets, I like to think of them, as in the PDF, as things for advertisements. So imagine these are all people here, right? Well, as an advertising agency, we don't have enough money to contact everyone. Instead, what we want to do is we want to find people that are highly influential. So what we can do is we can only talk to those people because we know that those few people are adjacent to everyone else in our larger graph. And so what a minimum dominating set is we're trying to find the minimum number of nodes such that from the nodes in that set, we're adjacent to all other nodes. So again, taking a look at the example of C and E, C is adjacent to F, D, B, and A, and then E is just by itself. So by including C and E, what we've managed to do is we can take the smallest number of nodes possible, and from either of these nodes we can traverse, or we're adjacent to any other node in the graph, right? So then, just like the advertising agency, right? We could just talk to people C and E, right? And then from C and E, they're adjacent to everyone else. So we're helping spread the word about our product. And so that's all a minimum dominating set is. But then again, how do we create A? How are we going to create this systems of inequalities? And well, A, for this case, is going to be all the nodes adjacent to a given node V plus V itself. So as you can see here, this first entry is for node A. And so as you can see, nodes A, B, C, E, and F are all 1s. And then for B, it's going to be A, B, C, D, E, and F is left blank, right? So what we're doing is we're taking all the nodes, including the node itself, so all the adjacent nodes plus the node itself, those are all going to be 1s. And so if you're looking carefully, this is actually really close to the adjacency matrix. The only difference for the adjacency matrix is that the node to the node itself is usually 0. So for example here, A to A is usually 0 in an adjacency matrix. So you should be able to figure out a way in order to take your adjacency matrix and change the A to A to be a 1, a B to B to be 1, etc. So all you're doing is just manipulating adjacency matrix again, just like in your clique. And it turns out, again, B is very simple. It's exactly the same as the clique again. You're taking just a 1s matrix. And so hopefully this makes sense. All you're doing is you're taking a node, you're saying all the nodes it's adjacent to, and then you're also including the node itself as being adjacent to itself. And then the final special type of subgraph we're looking at this week is called the k-plex. And so a k-plex is like a clique, but it's a little bit different. So cliques are something that's kind of hard to come by, right? If you imagine just a graph of a bunch of random nodes and edges, it's pretty challenging to find nodes that are all connected to every other node, right? Like, that doesn't happen that often. And so k-plexes relax the strict standards of a clique. And so I'm going to read off the definition that they have, and it's, so for each node V of a k-plex, if V is in the k-plex, then at most k minus 1 of the nodes that are non-adjacent with V can be in the set. And so, in simpler terms, this is just a clique but a little less strong. So, a 2-plex, right? 2 minus 1 is 1. So that means at most, one of these nodes doesn't have to be clique-like to all the other nodes. So as you can see here, A, B, and C is a clique, right? But then D is that one outlier node. It's almost a clique, right? But just D and A is not connected. And so D is the 2 minus 1, the one node that's a part of the k-plex that's not clique-like. And so that's all a k-plex is, just a less strong clique. And so this actually is the most challenging, right? Because it makes sense to like find node pairs that are non-adjacent, and it makes sense to like get all the nodes that are adjacent plus the node itself, right? Those are relatively simple tasks. Well, it turns out the math for the k-plex is harder. And so in order to complete it, the first thing we need to do is we need to create something called the complementary adjacent matrix. And so it sounds a little bit complicated, but it's actually a simple task. All we're going to be doing is we're going to be taking our adjacency matrix that we created earlier, and we're going to switch any 1 in that matrix to be a 0 and any 0 to be a 1. But we're going to leave the diagonal to be 0, so just the diagonal is not going to change. And so I'm going to leave you guys to figure out how to do that. And so I'm going to give you some hints. You're probably going to do a subtraction, right, to switch 1s to 0s and 0s to 1s. And then you're also probably going to use like an identity function or a diagonal function in order to make sure that that diagonal stays all 0s. And then once we have A sub C, or our complementary matrix, what we're going to do is we're going to create A. And I'm just going to give this line of code to you because it's going to be in the PowerPoint anyway. And so you can create a by doing this. So you take it diagonally, take the sum of a sub c, k minus 1, and then plus ac. And then, again, I'm also going to give you b, which is just the sum of a sub c. And so again, all we're going to be doing now is we're going to be taking the A matrix that we create in all three of these special types of subgraphs, and we're going to be plugging them into min-prog. And then min-prog is going to do all the work for us. So in some ways, this week's project is kind of tricky. If we are thinking about graphs as integer-wise, right, where nodes are either in or out of our special type of subgraph. But then again, this project's really easy because all we're going to be doing is you're going to be doing a lot of copying and pasting. All you're going to do is look at the project documentation, copy most of these variables, and then do a little bit of modification for each of the three types. Oh, there's one other thing I want to mention. You're going to be using another graph this week that you're going to grab from a .txt document this time. If you guys have any trouble, just come and talk to me. It's a little bit tricky grabbing data, and that's understandable because you're working from one format and you're converting it into a MATLAB understandable format. So just come to me during office hours or text me. And yeah, that's this week's project. Hope you guys enjoyed it.